we have done an RC circuit, we have done an LR circuit, so I think the only thing left in terms of these fundamental circuits is an LC circuit. That, of course, is a circuit that has an inductor and a capacitor, and we're not even going to put a battery in it. Let's just, what would happen if we just had this inductor and this capacitor staring each other down like that? LC. Well, let's apply Kirchhoff. I will rob him of one of his letters eventually. I think I've gotten it right so far. Kirchhoff loop. Well, okay, let's say the current is going that way. We want to loop that way. So we're going with the current through an inductor. Assuming the current is increasing, then you're going to get a back EMF. So we have minus L di dt. That's the potential drop across the inductor. And then here, current flows this way. Here's the positive plates. Here's the negative plates. And the drop across the capacitor doesn't depend on the current. It depends on the charge that is built up on the plates. So that's minus Q over C. So now I'm using little I for current, little q for charge. And we've gone all the way around the loop, so those are equal to 0. So right off the bat, we're in trouble. We have current as a function of time. We have charge as a function of time. And the current is already in a derivative. What a mess. So we know the way to get from one to the other is current is dq dt. So I guess what we have to do is write minus L d of dt of dq of dt minus q over c equals 0. And that is a second derivative. I'll go ahead and save myself a little space. This is minus L d2q dt2. So minus L times the second derivative minus q over c equals 0. All right, so now we just have to pull out our bag of differential equation tricks. Let's write it a little nicer and see if something comes to us here. We could isolate, usually in differential equations, you isolate the high derivative of the function d2q dt2 equals minus 1 over LC, comes over there, times q. That's where we are. And let's keep in mind that q is a function of time. We're looking for this function q. If we know the charge buildup in these plates, then we'll also know the current. We can just take its derivative. So we can find, I'll solve this for the charge buildup. We can solve it for the current. Doesn't really matter. But this is where we are. So we need to solve this differential equation for q of t. Our old tricks were maybe a substitution. Well, substitution is not going to help us here. Here's q and q all by itself. We would also put dq over q. Well, that's not going to do much for us because it's a second derivative. So it'd be d2q over q. Yeah, that's not going to work. So how to solve it? What do we do? Well, if you go in your freshman physics book, it doesn't really solve it. It just tells you the answer. Right? Maybe it gives you some physical intuition for why it does this, but it doesn't really solve it. Read the book carefully. It'll give you some circular argument about energy and try to trick you, but it doesn't solve it. So how do they really solve this in differential equations? Here is how they do it. I guess. You don't solve it. You can't solve it. How could you solve it? You can't integrate it because you don't know what it is. You can't solve it by integration. There are no tricks. You have to guess. Literally, you just make stuff up, and then you plug it in and see if it's true. If someone had told me that this is what we were doing when I took differential equations in 1991, I might not have gotten a D. But nobody told me that. I was very confused. But anyway, but don't worry, I retook it, and I got a C. OK, so we're going to guess. So now, how do you guess? This sounds like you need experience and practice. Yes, that you do. You don't just get these mathematically. You guess. Well, you look at it, and you say, well, what function is equal to its own second derivative to within a constant? And you just start making up functions and see what you come up with. So let's think. What function do we know is equal to its own second derivative to within a constant? Well, 1 might be q of t would be sine, right? Sine, derivative of sine is cosine, derivative of cosine is negative sine. So it does get back to itself, sort of, when you take two derivatives. Another, well, if sine does it, cosine does it. All right. That's a function that's equal to itself, to its own second derivative, to within a constant. The derivative of cosine is negative sine, derivative of negative sine is negative cosine. And they even bring in the negative sign, how convenient. Another one is the exponent, exponential function. Derivative of e to the t is e to the t. Second derivative is still e to the t, sort of equal to itself within a constant. So the next step in differential equations is you plug them in and see if they work. So that's what we will do next.